Right. Then we come to the types of joints in a chain. Types of joints. So I told you there are different types of joints. Yesterday we saw the classification of pairs, right? Now there are different types of joint. We'll see one by one, right? When two links are joined at the same connection, the joint is known as a binary joint. Right? Simple. If two links are joined, right? When two links are joined in a joint, that is binary. For example, a chain shown in figure 5.18 has four links and four binary joints at A, B, C, and D. A, B, C, D, these are four joints, and they are four binary joints. Why? One, two links are joined at a same connection, right? Two links are joined at a connection. So in A, link 4 and link 1 is connected. At B, link 1 and link 2 is connected. At C, link 2 and link 3 is connected. At 4, link 3 and link 4 is connected. Right? So these are joints where two members connected. So this is known as binary joint. Then we have ternary joint. Right?
How to identify it?
Ternary joint. When three links are joined at the same connection, the joint is known as ternary joint. So if three members are connected, then that is known as ternary joints. It is equivalent to two binary joints, as one of the three links joint carry the pin for the other two links. Okay. So here you see take like a joint E, and that is a ternary joint. Why? DE one member, EC another member, EA another member. So three members connected. So E is a ternary joint. Similarly, DC is connected, CE is connected, and CB is connected. So three members are connected at a joint. So this is a ternary joint. But this A and B and D, they are binary joints. Why? Only two members are connected. In D, DC and DE are connected. Similarly, at A, AE and AB are connected. And at B, BC and BA are connected. So these joints B, A, and D are binary joints, while E and C are ternary joints. Right? So ternary joints E and C, E and C, while binary joints which means like two members should be connected, right? So if you see the diagram, we have D, only two members connected, and we have A, two members connected, and I have B, there is also two members connected, right? So this B are different. This is for binary and that is joint. Okay, and one more statement is mentioned. This ternary joint is equivalent to two binary joints, right? So one ternary joint is equal to two binary joints, right? One ternary joint is equivalent to two binary joints. How is that? We'll see now how this is possible, right? So here, if I take the point E, where I have DE one member, EC another member, and EA third member, right? I have three members. Now I'm going to see how is it equivalent to two binaries. So this DE and EC are two joints, right? So if I consider for only these two members, this is a binary joint. right? Also, I can consider for EC and EA as like this. So for these two members, this is a binary joint, right? So this is a ternary joint. This is a ternary joint. I have three members connecting. At the same time, I can break it into two binary members, right? ED and EC, there's a joint, so it can be considered as one member, right? One binary joint. And EC and EA, we can consider this as another binary joint, right? Similarly, I can break the C also for DC and EC, right? That is a binary joint. Why? Two joints are there, that's a binary joint. Similarly, for EC and the CB also, I can have it as a binary joint, right? So this is one ternary joint, but I have two binary joints. That's why this statement is made. One ternary joint is equivalent to two binary joints, right? Now we move to the quaternary joints, right? So quaternary joints are joints which have four members connected to a point, right? When four links are joined at the same connection, the joint is called as quaternary joint, right? So there should be four members connected in a joint in order to make that joint as quaternary joint. This is equivalent to three binary joints. Right? In general, when L number of links are joined at the same connection, the joint is equivalent to L minus 1 binary joints. So in this diagram, we'll see what are the quaternary joints. So there should be four links connected. Okay, there should be four links connected. So we'll see. So I will write Q as quaternary joints. So if I have four links, no, I don't have only three. G I have four, right? So G E one member, G F second member, G C third member, G A fourth member. So I have four links connected at a point. So G is a quaternary joint. Right? Similarly, I have C also. C F one member, C G second member, C A third member, and C B fourth member. So four links are connected. So C is a quaternary joint. Do we have any other quaternary joints? No. Right? And now we will go for ternary joints. Right? So ternary joint means we should have three connections. Right? Uh, Point F is a ternary joint. Right? So I have FE is there, FG is there, FC is there. Right? So F is a ternary joint. Similarly, I have A. Right? Point A. I have AG, I have AC, and I have AB, right? So that is another ternary joint. Do we have any other ternary joints? Yes, we have a B, right? In B we have BD1 joint, BC1 joint, and BA1 joint. So there are not joints, there are three links, right? BD1 link, BC1 link, and BA1 link. They are joined at B, so that is another ternary joints, right? Now we check for the binary joints. We have D is a binary joint, right? D we have only two members, DE and DB. So D is a binary force member. And do we have any other? No, right? So yeah, and E is also a ternary member. Yeah, E is also a ternary member. ED is there, EF is there, and EG is there, right? So ternary member E is also a ternary member. Right? So this is how we find the uh, we found the which joint is existing over there, right? Any other joints means we'll see A, B, C, D, E, F, G. That's all right. A, B, C, D, E, F, G. Yeah. In this diagram only, these one are there. And we'll look into this diagram, which is quite different from that. So what happened was, diagram is same. Only thing is, this link GC is removed from this diagram, right? GC is removed from this diagram. So if GC is removed, then here in this diagram we are not going to have any quaternary joints. Right? Why? Because F is a ternary joint, E is a ternary joint, C is a ternary joint, G is also going to be a ternary joint. Right? So the quaternary joints G and C, if I join it only, I can have quaternary joints. If I remove it, this diagram I will not have any quaternary joints. Right? So if you see this diagram, this is a locked chain, right? Locked chain having binary, ternary, and quaternary joints. So locked chain, I told you, which means it will not be able to move, right? It will look like a truss, right? So as like the roof works, right? As like the roof works, when the roof works happening, this girder, in order to withstand the force, you know, it will look like this, right? So if I consider this as the basic frame for the roof, probably we will have structure like this. This is in order to withstand the force from the members, right? So these all are like kind of lock joints. So these joints will not move, right? You can assume, right? This will not move. What will happen if the joints move? The roof will move here and there, right? We don't want that, right? So these are lock joints, and these are called as these are like three force members, right? 3-bar chains. Okay. So by joining this G and C, we are making a joint which can move, right? This mechanism which can move to a mechanism which is actually locked. So primary chain having binary and ternary joints. If this, if you look at this diagram, this can move, right? So I am giving a small change in angle for this AG link, right? I am giving a small change. I can rename it as G dash, okay? And this angle which was previously was theta, and now I consider it as theta dash, okay? So if it's a kinematic chain, it should move, right? It should move in a direction. So what will happen if I can move this G link here, right? This entire structure may move like this, right? E can come here as E dash, okay? D can go there, okay? And F can come somewhere here, okay? Right? There's a possibility to this kind of motion to occur, right? And this C may come somewhere like this, right? But since I lock this G and C, there is no possibility to move this one here. Why? Because this CB link at point C is pulling this one this way, right? And this GC link, if I am going to give some motion, this should move this way, right? If I am moving this AG this way, this CG link should move that way, right? But due to this CB pulling in this way, and there's a GC link is made, this will not move, right? If there is no GC, then this can move, right? Since there's a GC, this will not move, right? Due to this, the kinematic chain which is in the picture B now turned as a locked chain, right? So locked chain means there won't be any movement. Okay. And about this binary joints here, right? So number of binary joints we are going to see, right? At ternary joints. So G and C are the ternary joints I told you. So G, E, and E, F, they are one binary joint. G, F, and G, C I can consider as another binary joint. G, C, and G, A I can consider as another binary joint, right? So what's mentioned here, it is equal to 3 binary joints, right? So this is one binary joint, other one is other binary joint, and the third one is third binary joint, right? Similar way, you can look at the joint C also. There I have FC and GC, one binary joint, GC and GA, another binary joint, CA and CB, third binary joint, right? We can have 3 binary joints here, right? So one quaternary joint is equivalent to 3 binary joints. You can convert it into ternary joints also, right? So this G point I can take GE, GF, and GC as one complete ternary joint, and GF, GC, GA as another ternary joint. I will erase that. Oh no, I'll put it in another color, right? So this GA, GC, GF I can consider as one ternary joint. Okay, GE, GF, GC I can consider as another ternary joint. Similarly, I can do here also, right? So a quaternary joint can be made into 3 binary joints or 2 ternary joints, right? And for binary joint, there is a common equation. So L minus 1 binary joints. So if L is the number of links are joined, right? L number of links are joined. So if 4 number of links are joined, that is quaternary joint. If 3 number of links are joined, that is ternary joint, right? If L number of links are joined at the connection, the joint is equal to L minus 1 binary joints, right? So if 4 links are joined, then it is equivalent to 4 minus 1, that is 3 binary joints, right? Similarly, if 3 links are joined, then 3 minus 1, that is equivalent to 2 binary joints, alright? So this is quaternary joint. Any doubt with this? Right. Now we will go into the next subtopic, number of degrees of freedom of plane mechanisms, right? Number of degrees of freedom. So first one you see is a 4-bar chain, and the next one you will see is a 5-bar chain, right? So number of degrees of freedom. So which means how many directions it can freely move. Okay. there are a few formulas and equations to find that, right? We'll come to that, right? So physically or like application wise, I'm telling you. So in 4-bar chain, this angle theta is enough to define the motion of all three other links, right? I can draw. Say for example, you are giving theta a small push and making that as some theta dash. Okay. So what will happen? This may come like this. So this D may take the position of D dash and C may take the position of C dash. Alright. This is D dash and this is C dash. And this change in angle, you can say theta dash. Alright. When this theta turn as theta dash, right? When the theta turn into theta dash, the angle ADC, right? Angle ADC, which is facing some change in angle, right? And angle DCB, which is also facing some change, right? We can calculate, right? That will move into numerical part, we'll do that. What I want to say is this change in angle theta to theta 1 can define the motion of D and C on a plane, right? But in the case of a 5-bar chain, the angle theta 1 alone is not enough to define the motion of this mechanism, right? We need theta 1 and theta 2 in order to say what would be the motion, right? Why? Because there are more than one possibility, as I told you. Say for example, now I am making this into this position, right? So this may take something like this, and this may go there. Okay, this is one possibility. Similarly, there can be another possibility also, right? So I will take this one outside now, outside in the sense like, yeah, like this. So I am taking this one like that. Right. So blue is the original position. Orange can be one possibility, and dark green can be another possibility. Right. So to define the motion of the joint E, joint D, and joint C, the theta 1 alone is not enough, right? I need theta 2 also. If the theta 1 and theta 2 is given, then I can find the change of angle of the other joints, right? So now we'll come into the formula section, right? How can we find this one numerically and what are the formulas available? So this is what actually meant by the degree of freedom of plane mechanisms, right? For that we have a formula which is called as Kutzbach criterion, right? N is equal to 3 into L minus 1 minus 2j minus h. This equation we will apply in order to find the plane mechanisms, right? So here few simple mechanisms are given. First one simple 3-bar chain, second one simple 4-bar chain, third one simple 5-bar chain, and fourth one is again a 5-bar chain, right? But in a different way. Fifth one is a 6-bar chain, right? So we'll apply this formula in order to find this 3-bar. In order to find the criteria, right? So we'll apply the formula. N is equal to, so n is a number of degree of freedom, okay? right? As shown in figure, 3 links, 3 binary joints, right? This J is number of binary joints, okay? So N number of freedom, L number of links, J number of binary joints, okay? Only binary joints, huh? And H is higher pair that I will explain later. We don't need it now because higher pair I told you yesterday. That is not going to be applied anywhere here. That's going to be 0 for all these diagrams, right? We'll put it in the formula, right? First one is a 3-bar chain, right? So the mechanism as shown in figure has 3 links, right? 3-bar chain. So which means it has 3 links and 3 binary joints, right? 3 binary joints. So here binary joint 1, binary joint 2, and binary joint 3. So 3 binary joints, links, link 1, link 2, and link 3, right? So I'll put it in the formula. N is equal to 3 into L is link, right? So that is 3 minus 1 minus 2j, that is 2 into number of binary joints, that is 2 into 3. 2 into 3, right? Minus h is higher pair that we don't need now, so I will put 0. So when you solve this will come 3 minus 1, 2, 2 into 3, 6, minus 2 into 3, 6, 6 minus 6, that is 0, right? So which means there is no movement. So degree of freedom is 0, which means it will not move, right? So this is what called as lock chain, or you can call it as a truss also, right? Then we have a 4-bar mechanism, right? I will put it in the formula. So formula says, I will change the color, 3 into L minus 1, right? At least number of links. So I have 1, 2, 3, 4 links. 4 minus 1 minus 2j, that is 2 into number of binary joints, right? 2 into number of binary joints. So binary joints I have C, D, A, B, that is 4 binary joints I have. So 2 into 4 minus H is 0. When you solve it, I have 4 minus 1, that is 3, 3 into 3, 9, 9 minus 2 into 4, 8, that is 9 minus 8 is 1, right? So this 4-bar chain I have number of degree of freedom is 1, right? So which means it can move in 1 direction. Then we come to the 5-bar chain, right? So again I will change the color. Again same formula, that is 3 L number of links, so 5-bar chain, that is 5 links, minus 1 minus 2j into, right? 2 into j number of binary joints, that is 5, right? 2 into 5 minus 0, right? Minus 0, which is equal to 0. So which will give you, once you solve it, 5 minus 1, 4, 4 into 3, 12, 12 minus 10 is 2, right? So here the degree of freedom is 2, right? And then it comes to this 5-bar mechanism, okay? This 5-bar mechanism, this is kind of quite different from the other 5-bar mechanism, right? So here the binary joints are 1, 2, 3, 4, 5, 6. Formula 3 into number of links. Since it is 5-bar, I have 5 links, minus 1 minus 2j, right? 2 into number of binary joints. So here number of binary joints are 6, right? As I drawn here, 1, 2, 3, 4, 5, and 6, right? So 2 into 6, that is 12. minus h is 0, I told you. So when you solve it, this will become 5 minus 1, that is 4. 4 into 3, 12. 6 into 2, 12. 12 minus 12, 0. Right? So there won't be any motion in this. Right? Why? If it is a 4-bar chain, that may move. But since I have joined A and C, this is not going to move. Right? This will not move. Why? There is a member which is restricting the motion is in the AC, which is restricting the motion. Right? So this 5-bar mechanism here is a lock chain. Right? This is not going to move. Then I have another 6-bar mechanism. This is also a different type of structure, you see. So here we have number of binary joints 1, 2, 3, 4, 5, 6, 7, and 8. Right? So I have 8 binary joints. Right? And links I have 1, 2, 3, 4, 5, 6. Right? 6 links. Then I will put it in the equation. I'm running out of colors. So 3 into, put it in the equation, L minus 1, number of links, that is 6, minus 1, minus 2j, that is 2 into number of binary joints. Right? So binary joints I have counted as 8. Right? 2 into 8 minus h is 0. Right? H is 0. So I will have minus 0. So when I solve it, 6 minus 1, that is 5, 3 into 5, 15, minus 2 into 8, 16, 15 minus 16, that is equal to minus 1, right? So there is a comment regarding this fact, right? So if it is 1, then there is 1 degree of freedom. If it is 2, then 2 degree of freedom. If it is 0, then there is no degree of freedom, it won't move. How about minus 1, right? How about minus 1? Here we will not have a minus output, right? So either it can move or it cannot move, right? We can't say it will move in minus, right? There is no minus movement. So what we have to assume is, if 0 is no movement, then the numbers below 0 is also there is no movement, right? So 0, there is no movement, means then numbers or results what we are obtaining below 0 also there is no movement, right? So this is how we find the degree of freedom using Kutzbach criterion, right? This is a Kutzbach equation. N is equal to 3 to L minus 1 minus 2h, 2j minus h. Right? So this h is 0 for points, right? Now we will see where we use this h, right? If there is any surface coming to action, then we will use this h. In any of these ways, there is no surface, all are only points, right? So until then, if you have any doubts, just comment. Or else we can move to the next slide. Okay. Yeah, right, fine. Then we will move. Yeah, so this is the solution solved, right? So if my writing is not that clear, so here we have the typewriter formula. So first one is a 3-bar chain, that is no freedom, right? Then 4-bar mechanism, that is 1 degree of freedom. So now from here onwards we can say DOF. DOF it stands for degree of freedom, DOF. Then 5-bar chain, 2 degree of freedom. Then the lock chain, because there are 2 binary joints at B and D. So I told you there are number of binary joints are increasing, right? So that's why this could not move. And here also the motion is restricted, right? Right. Here we have two examples where we have the h, right? Right. So here, if you see in between the points, I mean members 2 and 3, there's a kind of surface contact or line contact, you can say, right? So criteria with the higher pair or 2 degree of freedom, right? So now we will put this one in the equation, right? So n is equal to 3 into L minus 1 minus 2j minus h, right? That's the formula. So here, three link member, one link, second link, and third link. There are three links. So I substitute in the equation n is equal to 3 into L, that is 3 minus 1 minus 2 into binary joints, right? 2 into number of binary joints. So that is 2, right? Minus 1, that is minus h. So here there's a higher pair, right? So that's why I put h as 1, right? So now when you solve it, 3 minus 1 is 2, 3 into 2 6, minus 2 into 2 4, 6 minus 4 1, sorry, 6 minus 4 is 2, 2 minus 1 equal to 1, right? So when this higher pair is coming into action, this will not consider as a binary pair, right? So that's why here I used binary joints as 2. So actually what will happen, if it is 3 links, then we can consider one binary joint, second binary joint, and third binary joint, right? When this binary joint is acting as a higher pair, right, we can add this one into higher pair and we should reduce that one from the binary joints. So I have binary joint 1 and binary joint 2 here, right? So here only I have two binary joints and this one is the higher pair which is not binary joint here. Alright. So when you solve it, it can have 1 degree of freedom. So which means when this one rotates, right, like this, what will happen? This bar can slide over there, right? So this may move this way and this way. Up and down it may move. When this right, so this may move this way and the other way, right? This one will keep on rotating like this, right? Similarly, we can look into here also, right? So this is a kind of type of a toy, you can say, a weaker man, right? So again we will apply the formula, right? So here is again surface in contact. So n is equal to 3 into L minus 1 minus 2j minus h, right? So n, that is 4 links, right? Link 1, link 2, link 3, and link 4, right? 4 links, so that is 3 into 4 minus 1 minus 2 binary joints, 2 into number of binary joints 1, 2, and 3. Here surface is in contact, right? So I am not going to take this as a binary joint, this is going to be a higher pair, right? So that is 2 into 3, 3 binary joints only, minus 1. That one is this higher pair h, right? So when I solve it, I have 4 minus 1, 3, 3 into 3, 9, 9 minus 2 into 3, 6, 9 minus 6 is 3, 3 minus 1, that is 2, right? So here the degree of freedom is coming as 2, right? So why this is coming as 2, which means it can exhibit two motions, right? This can exhibit two motions. So one motion is moving forward, right? So when this is turning into some angle like this should move there, right? So this can be one movement moving forward, and there is another movement also, that is the rolling movement, right? This wheel is rolling now, so this is moving forward as well as it is rolling. So there are two motions, so there is 2 degree of freedom, right? So this is where we apply this H or higher pair, right? If some surface is in contact. Alright. This is also Kutzbach criteria. So in the previous slides we saw it for joints like pin joints, and here we use it for some other type of examples, right? So this is application of Kutzbach criteria. So this one we use to find the number of degree of freedom. Alright. Right. Then we come to the inversion of the mechanisms. Right. Inversions of the mechanism. We can obtain as many mechanisms as the number of links in a dynamic chain by fixing in turn different links in a dynamic chain. So if you remember when we were discussing about the compound dynamic chain, right? Compound dynamic chain, I told you by fixing certain links we can make different type of motions as we wish, right? So this is how that diagram was, I think, right? So for that one you can have by different fixing different links you can have different motions, right? So I will name these points as like A, B, C, D, and E, F, and G, right? So based on these, I can fix whatever the link I wish. Right? I can fix the link AG, or I can fix the link AF, or I can fix the link FE, right? Based on which link I fix, there can be different motions, right? There can be different motions. So this inversion of the mechanism means by fixing different links in a chain, this inversion is occurring, right? So this can be used for different mechanisms. Say for example, you have a simple 4-bar chain, but even in a 4-bar chain, by fixing different links, you can make different type of motion that we are going to look in the forthcoming slides, right? So we can obtain as many mechanisms as the number of links in a kinematic chain by fixing in turn different links in a kinematic chain, right? This method of obtaining different mechanisms by fixing different links in a kinematic chain is known as inversion of the mechanism, right? So we fix different links to obtain different mechanism is known as the inversion of the mechanism, right? Simple. We fix certain links based on our wish, right? And obtain different motions. That is known as inversion of the mechanism. Alright. It may be noted that the relative motions between the various links is not changed in any manner through this process of inversion, but the absolute motions may be changed drastically. Right? So there were two things we discussed. One is relative motion and the other one is absolute motion. Say for example, I fix this link, right? I fix this link and I am going to talk about the motion of AB, right? So I will talk based on the link AF. So if AF is fixed, then I can say AB has moved an angle theta. Then I need to say relative to what now? Right? So AB has moved an angle theta related to AF. Something I have to say, right? Just assume if AF is also rotating when you are rotating AB, then there is no any motion, right? If AB is also turning by theta, and then AF is also turning by theta, then there is no relative motion, right? So we need a reference plane to say relative to which or what link the motion as occurred. Right? So here it may be noted that the relative motion between the various links is not changed in any manner. Right? So the relative motion is going to be same, but the absolute motion may change. Right? So if I fix this link and making this to move, right? This is one phenomena, right? I can call it as one inversion, right? And a similar mechanism, right? Exactly similar mechanism. I will fix this link and move this link, right? So the relative motion, there's no change, right? But the absolute motion, that would be changed. Absolute motion means motion of that particular individual member alone, right? Say for example, I am not fixing that link. I will fix this particular link. What will happen? So now I am going to fix this link, and maybe this link will move, right? So here this link moved, right? So it has some velocity, some acceleration, and those vectors. But here that link is fixed, so there is no any movement, right? So here it has some velocity, but here it's zero, right? So the absolute motions may change, right? Absolute motions may change, but relative motions, there won't be any change, right? Relative motions, there won't be any change. So as a whole, the structure, the relative motions, there won't be any change. But these absolute motions, yes, there will be changes, right? So now we'll see one by one the inversions, right? Different inversions are there, and we'll see what are the inversions and we are going to use it. And these are few inversions, right? 4-bar chain or quadric cyclic chain, single cytochrome chain, double cytochrome chain. These are few inversions. Let's see one by one. So now we'll go for the first one. That is 4-bar chain or quadric cyclic chain, right? In a 4-bar chain, one of the links, in particular the shortest link, right? So if you consider this as a 4-bar link, this is the shortest link. Right? This is the longest link, and these two are two other links. So we are going to form a formula. This, right? One of the links shortest will make a complete revolution relative to the other three links, right? If it satisfies the Grashoff's law. So we'll see what is this Grashoff's law is, right? That we'll see later. Now we'll see these phenomena what's actually happening. Right? So this is the shortest link. This can make a complete revolution. This can. It does not mean this should make. It can make if it fulfills the Grashoff's law. Right? The Grashoff's law condition is S plus L is lesser than or equal to P plus Q. Right? This S means shortest link, L means longest link, P and Q are other two links. Right? P and Q are other two links. Either this can be P, this can be Q, or this can be P, this can be Q. Doesn't matter. Right? It doesn't matter. But S and L are fixed. Right? The shortest and longest members. Right? So if S plus L is less than P plus Q, then the shortest link will make a complete revolution, right? This is one fact regarding this inversions. Right? So based on these facts only, we are going to determine which inversions we need and how to form them, right? Such a link is known as the crank or driver, right? AD is the driver. So whatever the link which is making a complete revolution is known as the crank, right? So several mechanisms you might have seen like this a piston, right, flywheel, crank. So they are also the more body member which is making the complete revolution, that is the crank. So here also the member which is making the complete revolution is the crank. So which means the shortest link would be the crank, right? Shortest link would be the crank. Then the link BC, which makes the partial rotation or oscillation, is known as the lever or rocker or flower. Link BC, right, which is making a partial rotation or oscillation, right? So what will happen if this one rotates like this? This BC is there, or this BC will go like this, right? So we'll move that way and this way. So this is making a kind of partial oscillation, right? Since this is fixed, it can only oscillate this way and this way, this way and this way, right? So this is known as lever or follower or rocker, right? You can call by any one of this name, right? And the link CD, right? CD, there is a CD, which connects the crank and the lever is called as connecting rod or coupler, right? So here I have the crank, here I have the rocker or follower, and the one which is connecting these two is known as connecting rod, right? And then finally the fixed link AB known as a frame of the mechanism, right? And this link AB, this is not going to move anywhere. So on this link only, this complete mechanism is made, right? AB is fixed and relative to AB, all these motions are happening, right? AD is rotating relative to AB, BC is oscillating relative to AB, and DC is making some motion related to AB, right? AB is the fixed link. So AB is known as the frame of the mechanism. When the crank is the driver, the mechanism is transforming rotary motion into oscillating motion, right? So when the crank, right, this is the crank or driver, the mechanism is transforming rotary motion. So here, driver means the person who is driving a bus, right? A vehicle. Driver means who is the person who is driving that vehicle. Those who are sitting inside, they are called as passengers. So similar way, here also, whatever the mechanism which is driving, the mechanism is the driver, right? So most of the mechanisms, crank is the driver, right? So crank, when it drives the mechanism, the rotating motion, right? So here what's happening? Crank is making a rotating motion, and here the follower, which is making a kind of oscillatory motion. So the rotating motion of the crank is transformed as oscillatory motion of the follower. Right? Just imagine if I have a cut, right? A gutter here, right? If I have a gutter here and I fix something, a kind of you know something like this, right? What will happen? So when this one oscillates this way and this way, this will reciprocate, right? This will reciprocate back and forth. All right. So here the rotary motion is transformed into reciprocatory motion, right? So like this, we can make different types of motions, right? So based on our requirements, we can fix certain links, right? And we can make different types of motions, right? So when the crank is the driver, the mechanism is transforming rotary motion into oscillatory motion, right? So now this rotary motion is transformed as the oscillating motion. Right? So now you compare these terms with what the terms you refer in the automobile, this piston crank ring, that section, right? So the driver is the crank, right, which is making the rotary motion. Then there's a connecting rod. So connecting rod, it's connected with the gauge pin with the piston, right? And the piston is making a reciprocating motion. So that's the follower, right? The crank is the driver, piston is the follower, right? And there's a connecting rod between these two to connect them. and these all fixed in a frame, right? That frame is here, AB, right? So this actual phenomena is based on this 4-bar chain, right? The actual phenomena is based on 4-bar chain. So this is how we look into the applications of this inversions, right? So inversions are actually made up for the application. So basic theory is there, that's basic, right? Now we are going to develop from that, right? So this is 4-bar chain, or you can call it as quadricyclic chain also, right? There are three possible mechanisms, right? In 4-bar chain, there are three possible mechanisms. They are double crank mechanism, double rocker mechanism, and crank and rocker mechanism. So as I told you in the previous slide, a crank means the part which is making a complete rotation, right? So the part which is making the complete rotation is known as the crank, and the part which is oscillating can be this follower, right? And this could be the frame, all right? I will take this as a kind of reciprocating motion I am bringing, right? So this is frame. Okay. So here we have a crank, a connecting rod, and a follower or rocker, right? So this is the basic. So there are three possibilities, right? One is double crank mechanism. So which means there should be two rotary motions existing, right? Two rotary motions. Other one is double rocker mechanism. So which means there is no rotary motion at all, but only oscillatory motions, right? So double crank mechanism means there should be two complete rotations to occur, right? So based on each part, there should be two complete rotations, right? Two parts or two members should exhibit the complete rotation. So if I consider this as the frame and this as the connecting rod, right? So these two should make a complete revolution. That is what mentioned by double crank mechanism. There should be two cranks, right? And there is another mechanism called double rocker mechanism, right? So double rocker means there is not even a single crank, right? So which means there is no crank motion, right? So there is no rotary motion, only reciprocating motion is there, right? So double rocker means this one is moving a partial oscillation, this one is making a partial oscillation. There is no complete rotation. And third one is crank and rocker mechanism. So there I have a crank which is making a complete revolution, and there is a rocker which is making a oscillating or like reciprocating motion, right? So these could be the three possible mechanisms, right? Uh, One is double crank, so that should exhibit two complete rotations. The other one is double rocker, right? There is two possible like oscillatory motions, and other one is crank and rocker mechanism. All right. So these are the three possible mechanisms for this inversions, right? So here is one example, right? So for the double crank. So when you observe this one, these links, right? Which links? Link red color and the link a kind of light green. These two are making a full rotation, right? Full rotation. That is double crank. So there you see L is the largest link, S is the smallest link, right? P and Q need to be there, right? So here the shortest link is fixed, right? In double crank mechanism, the shortest link S is grounded links, right? Grounded links mean fixed link, right? Grounded link mean fixed link. Both input crank and output crank rotate at 360 degree, right? So if you fix the shortest link, then both input and output crank rotates at 360 degree. So the condition for double crank mechanism is, right? Condition for double crank mechanism is shortest link should be fixed, right? Shortest link should be fixed. In the previous slide, you saw another criteria, right? S plus L should be less than P plus Q if one link should make a crank. At least one link should make a crank. Then that criteria should be fulfilled. Right? So for double crank mechanism, the shortest link should be grounded, right? This is the formula for double crank mechanism. Then we have double rocker, right? For double rocker mechanism, S plus L should be greater than P plus Q, right? S plus L is greater than P plus Q. Right? So you can see these two arcs. Right? These two arcs are the true. Right? So the condition is for double rocker. That is for both the crank, both the arms should make a partial rotary motion, which means there is no complete revolution motion. Right? So here the condition is S plus L to be greater than P plus Q, right? So S is shortest link and L is the longest link. That should be greater than P and Q. P and Q are the other two links, right? In double rocker mechanism, the shortest link S is the coupler link, right? So S is the coupler. Coupler is the connecting rod, right? So if this one is the input, then this could be the output. Or if this is the input, this could be the output, right? So only four members. One is fixed link, Q is a fixed link, right? So if I consider P as the input, then I will have L as the output, right? If I have L as the input, then I have P as the output. So the one which is connecting these two will be the connecting rod or coupler, right? So for double crank mechanism, the shortest link should be grounded. For the double rocker mechanism, shortest link should be the coupler. That's the second mechanism, right? Double rocker, right? here the shortest link is going to be act as the coupler, right? So either we can consider this yellow as the input or red as the input, right? So I'll take yellow as the input, right? So this yellow can go only up to this particular position, right? It can't, right? So this would be the maximum length between these two joints, right? Both the links pivotal to the fixed link oscillates. Why? Because this one also can't go beyond this because this is now the maximum length, right? And this one also can't go to this other side because that's the maximum length, right? So only within this length range it can exhibit any motion, right? So this is why it is creating a double rocker mechanism. For this one, the condition is S plus L is greater than P plus Q, right? Shortest length plus length is so longest length or link you can say, right? Shortest link plus longest link would be greater than P and Q. These are other two links, right? So if you really wish to like observe how is it working, you can like take four small rods and fix according to this condition, right? You take a ruler and measure these things, right? And fix it and try to make this move, then you will realize how is it moving. And if you want, you can do one more thing, right? In these joints, right? Only in these joints, that's moving joints. Here you don't need. This is fixed joints. In these joints, you fix a kind of a small pencil, right? Instead of nail or anything, you just fix a small pencil and let it move. So if you move it in a like white paper, this will create the motion, right? So when you by your hand, when you move this yellow link this way and this way, right? The fixed paper pencil in this joint and in this joint, that will create a motion, right? Or drawing. From that drawing, you can understand how is it moving. For that, this condition should be fulfilled, right? So you see, and now I will take red as the input, right? So what this red can do is it can go only up to this point. Why? When it comes to this point, that's at the maximum length, right? It can't go right. So at this point, right? At this point, the length is maximum. This can't go beyond that. This is already fixed. So that's why it is stopped with this, right? If it can go beyond this, then this will make a kind of motion this way, right? But it can't go. So that's why this is stopped with this, and now it's going to return to this position, right? Shortest link is the coupler, and that is making a full revolution, right? The shortest link, that is blue one. This blue one is making full revolution. You see, right? But we are not talking about the coupler here, right? We will be talking about input and output links. So this is what is double rocker or double lever mechanism. Right? Okay. So this is the double rocker mechanism, and the condition is S plus L is greater than P plus Q. So anybody those interested, you can try abiding these conditions. Which conditions? S plus L is greater than B plus Q, S plus L is less than B plus Q, S plus L is equal to B plus Q, right? Abiding those conditions, you take few rods. That's not a big task, right? Take few rods and in a small paper, you just move it, right? So there you can see how these motions are, right? Okay, right? Then we have the crank and rocker mechanism. So this one you have already seen. For that one, the shortest link, right? Shortest link will make the complete rotation, right? Right? Crank and rocker, shortest link will make the rotation. For that, the condition is S plus L is less than P plus Q. Right? Shortest link rotates fully, while the other one, ratio of linkage is S plus L is less than P plus Q. So S is the shortest, L is the longest. It should be less than P plus Q. Right? So here is the input S, and this is the output, that is P. Right? Position of other three links does not affect the nature of the mechanism. Right? So either Q or this can be Q, doesn't matter. S is the shortest and L is the longest. Right? And here you can be other two links. Right? So the condition here is S shortest link plus L longest link should be less than P and Q, their other two links. Right? So for the Frank and Roca mechanism, S plus L should be lower than the P plus Q. And this is the last specific type, right? Parallel crank mechanism, right? This is also double crank, right? This is also double crank, but this is parallel crank, right? These two cranks will not intersect each other. Parallel linkage mechanism is a special case of Redox criteria. This is special. Some of the shortest link S and the longest link L of a planar cortical cycle is less than or equal to the other two remaining P and Q. If it is making a parallel mechanism, you should understand that the red link and the yellow link is going to be equal in size, as well as blue and green is going to be equal in size. Right? So either green and yellow, red will be equal to blue and yellow, or green and yellow will be equal to red and blue. That's why it's known as a kind of special consideration, right? And so the coupler, there won't be any change in the orientation, right? So you see here, this coupler is going up and going down, going up and going down. There won't be any change in the orientation, that is change in the angle. So for this type of link, the condition is S plus L is equal to P plus Q, right? S plus L is equal to P plus Q, right? So based on changing these different linkages, right, and changing the lengths and changing the ground links or fixed links, we can make different types of motion. All of them are four bar mechanisms, right? Every link, every mechanism has only four links, but one is giving you double crank, one is giving you double rocker, the other one is giving you one crank and one rocker, right? So different mechanisms are possible, right? So this is why this four bar chain is a kind of importance, right? It has a different kind of importance since it can exhibit different types of motions, right? So this is the inversions